Well, good morning. We continue with liquid propellant rockets. Let us quickly recap where we were last time. We said feeding of liquid propellants can be done in different ways. One was, we said, using a cold gas. Cold gas could be used either in the blow down mode or in a regulated mode, right. The difference is, in a regulated mode we draw gas at high pressure, maintain a constant low pressure on the propellant and push it out. In the blow down mode, in the tank itself we have some volume of gas which is known as ullage volume, which is pressurized initially, and you allow this pressure to gradually push the propellant, in which case the pressure at which propellant is supplied into the thrust chamber will keep decreasing with time, right. While deriving an equation for the mass of gas required in the gas bottle, we found if the temperature of the gas is higher, it is better. Therefore, we also talked in terms of hot gas pressurization, right. But we told, even though it is advantageous, it has not been implemented so far and it will be worthwhile. In fact, there was one of the French engines which tried this, but they did not follow it up, but I think it is a strong contender. We also found out that when the time of operation of a rocket is small, or when the thrust is small, or when the chamber pressure is small, we can go for something like cold gas pressurization in either the blow down mode or a regulated mode or even a hot gas pressurization mode. But the moment the pressure of the chamber is large, or the thrust is large, or the time is large, we necessarily have to go for a pump fed system, right. We also found that the amount of power required from the pump is enormous, something like for a 600 kilonewton engine we found that the pressure required is, or the power required is something like 2.4 or almost 3 megawatt, and we said even a large power plant like the Ennore power plant has only something like, we said something like 450 megawatts of power. Therefore, we are talking of huge power, and therefore we cannot drive the pump using a battery or an electrical supply. And let's quickly therefore go through where we were. Therefore, we said in order to drive the pumps, we looked at this figure in the last class also. You have a fuel tank, you have a oxidizer tank, both are liquids. You sort of push this into the pump, maybe we need a gas bottle which pressurizes it to a small value, pushes it into the pump. I need to rotate these two pumps, for which I require a turbine. That turbine generates power and it pushes this. To drive the turbine, I need something like a gas generator or a hot gas source which powers the turbine and the hot gas is exhausted out. The pressure built in these two pumps pushes the liquid oxidizer, pushes the liquid fuel into what we said was the thrust chamber. What I am circling now is the thrust chamber. Now, to have an additional thing for a generating gas is difficult, because I need another set of fuels or another set of substances which can generate the gas, and the normal practice therefore is to make use of the existing fuel and oxidizer itself. How do we do that? We also looked at it in the last class. Maybe after you are pressurizing the liquid fuel, you take a little bit of the liquid fuel into something like a pre-burner or a burner over here, which we call as a gas generator. You take the oxidizer also, mix the two together over here, generate hot gases, push the hot gases into the turbine and exhaust the output from the turbine into the ambient. Therefore, you have something like a gas generator which is driving the turbine, which in turn drives the fuel pump and the oxidizer pump and supplies the fuel and oxidizer into the engine. Such a feed system being essentially configured around the gas generator, and how does the gas generator get the fuel? Maybe part of the fuel is bled, part of the oxidizer is bled from the lines, and it is used to generate hot gases. Now, there is a problem in all this. The turbines consist of blades, and it could be impulse turbine, reaction turbine, maybe we have to look at it. but whatever said and done, if I put very hot gases into the turbine and we said at stoichiometry the fuel and oxidizer generate gases at a temperature around 3600 degrees Kelvin, and therefore I cannot supply these hot gases, therefore the output of the gases from the gas generator must essentially be a small number, maybe around upper limit is around 900 Kelvin. Therefore, how do I do that? Maybe I use a very fuel rich mixture or a very oxidizer rich mixture in this gas generator and supply it, and the work done by the turbine is equal to the work done by the two pumps. This cycle is what we called as the gas generator fed gas generator cycle for feeding propellants, right. See, unfortunately, when we learn thermodynamics, we say cycle is something wherein things come back to the initial state we call as cycle, but this is just something like what we are saying is it's using a gas generator we are feeding propellants. Unfortunately, the word cycle has come over here. It is not related to the thermodynamic cycle like an Otto cycle or a Joule cycle or a Brayton cycle. No, it is just a gas generator fed system, but in conventionally it is known as a gas generator cycle for feeding propellants, and I use the same terminology. We also told ourselves in the last class, well, this is what I had in mind. See, we said that the temperature of the gases as a function of mixture ratio is such that the maximum temperature occurs just below the stoichiometric, and therefore you had a slight shift. Instead of maximum temperature occurring at stoichiometry, it is slightly fuel rich, but when we need a much lower temperature, maybe I have to operate the gas generator in a very fuel rich region such that I get only around 800 to 900 Kelvin, or maybe a very oxidizer rich region wherein I get a low temperature. Oxidizer rich region is seldom used, but many of the Russian engines do use oxidizer rich. But the reason why oxidizer rich is not conventionally used is if you have something rich in oxygen, it can always oxidize a metal, whereas if it is fuel rich, it cannot oxidize a metal. Therefore, maybe the trend is to use a fuel rich mixture. Therefore, this was in the context of the choice of the mixture ratio for the gas generator. We tell ourselves I use a fuel rich mixture which has a maximum outlet temperature from the gas turbine or the inlet to the turbine around 900 Kelvin. Well, this shows an example of it. I have a small gas bottle which pressurizes the, let us say, the fuel and the oxidizer. It is fed into the pumps. I also bleed a little bit of fuel, a little bit of oxidizer, burn it in a gas generator. I generate hot gases, and these hot gases drive the turbine, and when it drives the turbine, in this particular schematic you have a gear train changes the speed and hence the torque required for the pumps, and these two pumps supply the propellant to the engine, and the same thing is bled off here. You may ask me, how do I start the engine? After all, I need high pressure over here. Maybe I need another bottle of high pressure gas or maybe some slug somewhere, which I initially use to rotate the turbine, and once it rotates maybe it starts pumping and then I shift to this. That is during the initial transient. Well, this is all about the gas generator cycle. We will get back into it in some detail to find out what is its performance. We have discussed the feed system cycles in the last class and said that the term cycle, which usually refers to a thermodynamic cycle, is really not valid. There is, however, a cycle known as topping cycle used in power plants. Let us say the Rankine cycle, which is used in power plants. What is it we have? We have a boiler which generates steam. The boiler runs a turbine, that is the high pressure steam runs a turbine, and that is what generates your particular power over here. And then the outlet from the turbine is fed into the condenser wherein water is condensed, and then you have a pump which pushes back the water into the boiler, boiler heats it, and this is what is a Rankine cycle. Now, very often what is done is to improve the efficiency. We know Carnot efficiency is when the temperature is a maximum. Now I am taking the cold water, increasing the temperature, then supplying heat, and then I am doing this cycle. If I were to bleed part of the, after a part of the expansion, I bleed some of the gases, I take it into something like a feed water heater and use this feed water heater, that is heated water, into the boiler. Well, my efficiency will increase because my net temperature is higher, and this scheme is what we know as, what we call as the regenerative Rankine cycle, right. Just like you have regenerative cycles, essentially what you do is you heat the water before you do this. And how do you heat? You bleed some of the partially expanded gases in the first turbine, allow it to heat the feed water, and then you pump the feed water, and anyway this part of the cycle also continues. Therefore, you are essentially able to get a higher efficiency, and these cycles are known as regenerative cycles. We also learned in terms of cogeneration cycles. And what do you mean by cogeneration? Maybe I bleed some of the hot gases from of steam coming over here, maybe at saturated level, use it to heat houses, heat it, use it for some other purposes, and that is what is known as cogeneration. That means instead of allowing the heat, and how do we dissipate heat in a condenser? Maybe I have something like a tower in which I allow the water to drip, I allow the hot gases to go, the hot gases transfer the heat, I mean the hot steam condenses over here, it heats the environment, that means it heats the water. Instead of doing that, you know what we could probably do is, instead of heating the environment, I allow the steam to go and be usefully used for heating houses, for heating some places, maybe some industry for heating, and that is known as cogeneration. These two cycles are also known as the topping cycle. Why we say topping? Because you use some of the heat for topping up your processes, whether for heating the houses or for improving your efficiency, and this is known as the topping cycle. Well, if we talk of topping cycle, we should also talk in terms of bottoming cycle. What is that? Maybe if I have a furnace which is generating very high temperatures, and I use this furnace to heat some product, tempering steel or maybe for steel making or whatever it is, and instead of allowing the exhaust gases from the steel making plant to be dissipated into the environment, I use it to generate steam, then it is a bottoming process. It is just the opposite of your generation, but I use the waste heat from your furnace to generate steam and therefore to generate power or to generate electricity, and this is known as the bottoming cycle. Therefore, when I consider topping cycle, can I use some element of topping cycle in the gas generator cycle which I just talked of? Let's just try to put it together again. We must be very clear about it because these feed system cycles are important. I have something like a gas bottle. From the gas bottle I have these two tanks, fuel tank, oxidizer tank, let us say fuel oxidizer. I take the fuel into the pump, I take the oxidizer into the oxidizer pump, and then I push it out. Why is this gas bottle required? I need some minimum pressure to push it out, therefore now my requirement of gas is much smaller because my pressure is going to be smaller. And then before I take this fuel pump over here, I take the pressurized fuel into something like a gas generator over here or a pre-burner or something which generates hot gases at a mixture ratio which produces not a very high temperature. Similarly, I take the oxidizer into it, I make it react and generate the required temperature gases over here, and the balance I sort of put into my main combustion chamber, which I call as the main combustion chamber or main thrust chamber over here. Therefore, what is it we did? We have something like mass of fuel which is supplied by the tank, mass of oxidizer which is supplied by the tank, part of it I bleed into this, namely part of the fuel I bleed into the gas generator, part of the oxidizer I call it as MO I put into the gas generator. Now the balance what comes over here is m dot f minus m dot f into what has been supplied to the gas generator. What comes over here is m dot o, that is the main which is coming, something has gone out, minus m dot o into the gas generator. Therefore, what is it I am talking of? I am talking of when the overall mixture ratio is the overall fuel and oxidizer which is supplied to your system or to your overall rocket engine is something like a mixture ratio I call as mixture ratio R, which is equal to m dot o by m dot f, mass of oxidizer divided by mass of fuel. What is the mixture ratio of your gas generator? R gas generator is equal to m dot of O, which gets into your gas generator, divided by m dot f, which gets into your gas generator. Then we said this mixture ratio must be terribly on the fuel side, because we told ourselves, well, the temperature versus mixture ratio, if I were to plot, instead of MR I am writing R, is something, this is something like stoichiometry, this is the peak temperature, maybe I want a reduced temperature, I operate on a fuel rich region, or I have to operate somewhere over here which is the oxidizer rich region. Therefore, now I write the value of the mixture ratio in your main chamber which generates the thrust, or let us say I call it in the main chamber RMC is equal to m dot O minus m dot O corresponding to the gas generator divided by m dot F minus m dot F, which goes into the gas generator. Therefore, you have 3 mixture ratios to contend with. I would like this mixture ratios such that I get maximum specific impulse, but if I were to overall look at it, I would like to choose this mixture ratio such that I get a good performance. Maybe we have to calculate this a little bit more carefully. Let's finish the topping cycle and come back to it. What is therefore this topping cycle? And this, what we had just now said, is what we call as the GG cycle engine, gas generator fed engine. Okay. I now ask myself, see, after all, what did this gas generator do? It drove something like a turbine, and what was this turbine? In the turbine I have high pressure gases, I reduce the pressure of gases to low value, and then I take the gases out, I exhaust it out through a nozzle. This is auxiliary. The temperature at the inlet to the turbine or outlet of the gas generator we said is typically less than 900 Kelvin. Therefore, the temperature at the outlet of your turbine will be even less, maybe around 400 or so, and therefore, the type of specific impulse which this expansion can give is going to be a small number. Let us call it as specific impulse from the gas generator, which comes from the exhaust of your turbine, which is expanded through a nozzle. Whereas the specific impulse corresponding to the main chamber, we call it as specific impulse of your main chamber. Therefore, what will be the total impulse what I get? It will be the fraction of propellant at this specific impulse plus fraction of the propellant at this impulse, and therefore, now I say if I were to find out what is the value of the total impulse what I get from this gas generator cycle, or total specific impulse, I call it as net value, is going to be fraction of the gases F of the total. That means I have m dot O plus m dot F, which is the total supply, divided by I have m dot corresponding to the gas generator plus m dot fuel corresponding to the gas generator, I define as the fraction F, and therefore this fraction into the ISP of expansion in your gas generator exit from the turbine, plus I have maybe 1 minus F, that is the part of the propellant which flows through the main engine, is equal to ISP of the main chamber. Okay. We told ourselves this fellow is slightly weak because the supply temperature is small, have expanded the gases, pressure is small, therefore the ISP of this will be very much lower than this, and therefore the net specific impulse of this, that means the total specific impulse of this gas generator fed engine is going to be less than the specific impulse what I would have otherwise got had I not done this. Therefore the question is, can I get this heat which is being wasted in a poor way, can I get it come into the chamber? In other words, it is very similar to the regenerative process in a Rankine cycle. Therefore, and that is what we say is a topping cycle, and let us put that together. Maybe I will leave this space for analysis of the GG. Let us put it together. I again have a gas bottle. It supplies the 2 tanks, a fuel tank, maybe an oxidizer tank, and then I take the things out over here, and here I have a fuel pump, increases the pressure. I have an oxidizer pump which again increases the pressure. I take the lines out, now this is high pressure, I have pump here for fuel, for oxidizer, and then what is it I do? I take some of the fuel at high pressure over here, take it into the gas generator over here, and then what I do is I use this to drive a pump turbine. I bring the turbine here, high pressure becoming low pressure. Let us keep the directions very clear. I also take a little of this, little of the oxidizer, allow it to come into the gas generator over here. Now the temperature of your gas generator is typically around 800 to 900 Kelvin, 900 is the upper limit, let us say 700 to 900 Kelvin, and this drives your turbine. And what do you do with the turbine exhaust? Now let us see how to regenerate it. And these two, the balance of the fuel and oxidizer, come into your main chamber. Now what do you do with this turbine exhaust? You bring the turbine exhaust out over here, and I also admit it into the injector over here. That means the heat which is left out in the turbine is again regeneratively used here, and this is what constitutes the topping cycle used for a feed system. In other words, the exhaust is not wasted with low impulse as in a gas generator cycle, but is fed back into the main chamber for secondary combustion. First combustion takes place here at low temperature, then turbine expands it, and then that is mixed with the other part of the process here, and therefore the combustion now takes place in 2 stages, and therefore this topping cycle is also referred to as combustion taking place in stages, or something like staged combustion cycle. Now we will try to find out what is the value of overall mixture ratio, what is the value of mixture ratio of the gas generator, what is the value of the mixture ratio in the main engine, just like we did for gas generator. Let us do it for the staged combustion cycle. Well, for staged combustion cycle, again we say m dot of oxidizer, m dot of the fuel. I supply something like m dot O corresponding to the GG. I take this was your fuel line, therefore I say maybe this should have been F, this should have been O, therefore I take m dot F into GG, I take m dot O into GG, and then here I had m dot F minus m dot F GG, here I had m dot O minus m dot O Gg, all this is coming back here, and therefore the net value what enters here is still m dot O and m dot F, or rather the overall mixture ratio, if it is going to be m dot O by m dot F, the mixture ratio in your main engine or main chamber is again the same value of m dot O by m dot F in this case. And what is the gas generator? Gas generator is equal to, like what we had earlier, m dot O Gg by m dot F Gg. This is the main distinction between a gas generator cycle and what we call as a staged combustion cycle or topping cycle. When we use the gas generator in the staged combustion cycle, very often it is referred to as a pre-burner, because it first burns and again we have a second burn. The cycle is also known as the gas generator is called as a pre-burner. Well, we need not even have something like a staged combustion cycle. When we talk of volatile fuels means liquid hydrogen, or let us say liquid methane or liquid propane. It is also possible for us to have another cycle. Let us quickly plot that out. Maybe I have a gas bottle, let us say I have volatile fuel, let us say liquid hydrogen or liquid methane or something like this. Maybe I have oxidizer like liquid oxygen. In this case, what I could probably do, and which is also workable, is maybe I have a pump over here, I have another pump over here for the oxygen. Now what I do is, this particular liquid hydrogen I have to supply to the chamber, combustion chamber. The combustion takes place in a chamber, it runs hot, and therefore I connect it to the chamber like this. The hydrogen flows along the chamber, gets heated, and this heated hydrogen I take it out over here. I run my turbine using this hot gases, hot hydrogen vapor or hot volatile liquid, whatever is generated, and then I drive the turbine, and then I take the exhaust gases, put it into the chamber, I take the oxidizer, put it into the chamber, and in other words, what is it I have done? I have a turbine which is run by the heated fuel or heated oxidizer, whatever be it is possible to generate a vapor. I generate the pump, I drive the pump, I drive the pump of the fuel, I drive the pump of the oxidizer, and in other words, just by using the hot chamber I expand the gases in a turbine and I run the pumps, and such a cycle is a derivation of staged combustion cycle, but without a pre-burner, and this is known as an expander cycle. Therefore, the pump fed systems are basically classified as belonging to gas generator cycle, in which case I allow the exhaust from the turbine to go into the environment. Maybe second is a staged combustion cycle, wherein I put a pre-burner and take the combustion to occur in 2 stages, or I just use the hot vapor generated on the outside of the engine. Maybe in the next class I will do the regenerative cooling, and it will become little more clear at that time. I use the vapor formed during cooling of the chamber to run a turbine. This vapor runs the turbine, and this turbine then runs these 2 pumps, which is known as an expander cycle. We could have combinations of some of these cycles, like we could also have, maybe instead of allowing the exhaust from the gas turbine to come through this, maybe I can feed it into the nozzle divergent and try to generate little more thrust, in which case the cycle is known as gas generator with bleed. What is bleed? I allow some of the output gases to come and generate little more thrust by injecting it into the nozzle here. You could keep on devising cycles, or maybe I could have something like a combustion taking place in the chamber. I allow the gases to come and drive the turbine. It is known as a combustion type of cycle, but it has never been used in practice. What has been used in practice is expander cycle. This is, you will recall I showed a cycle, I showed an engine RL10. I said this was the first engine, the first cryogenic engine developed in US. This uses an expander cycle. Most of the cycles use the gas generator cycle, but the stage combustion cycles are extremely powerful, have very high performance, as we shall be seeing subsequently, and this is what is normally preferred. I think we will take a look at it. What is to be preferred, when and why is what we must address. But to be able to do that, let us therefore now summarize whatever I have been telling so far in the following language. Namely, we said a liquid propellant rocket could either be pump fed or be gas fed. For gas fed, we know how to calculate the amount of gas either in the blow down mode, regulated mode, or in the hot gas mode. When we talk of pump fed, we told ourselves, well, gas generator cycle, stage combustion cycle or topping cycle, and the expander cycle. We would like to know under what conditions do I use this cycle, when should I use this, when should I use this. Well, we could have derivatives, gas generator with bleed, which wherein instead of allowing the gas to go to the exit, I allow it to the ambient through an auxiliary nozzle. I allow it to get into my nozzle and generate little more thrust, or I could also have something like a combustion tap off. I use the, instead of having a separate pre-burner, I tap off some of the products from the combustion. But you know, to be able to tap off the same consistent mixture ratio is difficult, and that is the reason why such things are not used. We have several other cycles which are not of interest, but I think we must keep our minds open and try to see how best we can improve these cycles. If this part is clear, I can go back and analyze what cycle should I use when. What is it? Let's do this exercise. We find that the gas generator cycle a fraction f is not very usefully used. Can I calculate that value of f is the first question. But before I do this, let us quickly run through what little I have been doing. I think this is whatever we are doing is related to the feed system and it is important. This is the topping cycle. Well, this is the expander cycle. In the expander cycle, you have fuel and oxidizer. The oxidizer is pumped with this pump, this is pumped over here. The fuel is a volatile fuel, therefore it comes, cools the chamber, the hot vapor so generated runs the turbine, exhaust from the turbine is fed back, and that is why we call it as the expander cycle. The vapor is generated during cooling of the particular thrust chamber. Well, this is gas generator with bleed. The exhaust, instead of being expanded through an auxiliary nozzle, comes back into the nozzle in the divergent portion, and it is used to develop some more ISP for this or some more specific impulse of your rocket. I think this is all about it. Let's now put things together. This looks clumsy, but it's exactly what I have been writing on the board. You have mass of fuel, mass of oxidizer, mass of this, and all that is all what is shown in this particular figure. This I show for the gas generator cycle. On this side, you have mass of oxidizer coming into the turbine. The part is taken to the gas generator. In this case, I consider the specific case of liquid oxygen, liquid hydrogen, mass of hydrogen coming into the pump over here. This is taken into the gas generator, burns here, drives the turbine. The balance what comes in here is only fuel, that is m dot hydrogen minus m dot, which goes into your gas generator. Similarly, you have oxygen which comes in here, which is equal to m dot of oxygen minus m dot, which goes into the gas generator. Therefore, in this case, in the GG cycle, to repeat again, you have three mixture ratios: an overall mixture ratio, a mixture ratio for your gas generator, and a separate mixture ratio for the engine or your main chamber. Whereas in your stage combustion cycle, the overall mixture ratio is same as the mixture ratio for your engine. The mixture ratio for your gas generator is bound to be different. Is this part clear? If this part is clear, let's quickly do this exercise of finding out what will be the value of f. See what is done over here. You know, I forgot to draw this line over here, we should have reminded me on this. What is this line? I say that the turbine is rotating, the turbine rotates the oxidizer pump, the turbine rotates this pump, because mechanically the power generated in the turbine is running these two pumps. Therefore, let us to be able to find out how much fuel is required or what is the fraction of propellant which is required to drive the turbine here, I need to be able to find out how much pump power is required. Therefore, let us put it down. What is the power developed by the turbine? And where does the power developed by the turbine go? It runs these two pumps, let us say pump for fuel, pump for the oxidizer, and this must be equal to the power required for the two pumps, right. Now, what is the power developed by the turbine? We were very clear, we told ourselves the outlet temperature from the GG is, let us say, 800 900 Kelvin, we call the outlet temperature as TGG, and this temperature of gases is what enters into your turbine. Let us say that the outlet temperature from the turbine is temperature outlet, let us say T outlet. I again repeat, TGG is the temperature at which the hot gases from the gas generator enter your turbine. Some power is generated in the turbine, there is some expansion, maybe an impulse turbine, you are expanding the gases, and at the outlet the temperature is T outlet. Therefore, what is the work which is done by the turbine? Rate of work is equal to m dot O Gg, the mass of oxidizer, mass of fuel into the Gg, that is the total propellant flow into the Gg, which is the total propellant flow into this, into the value of Cp, that is your enthalpy, and therefore this is going to be so much watts or so much, right. M dot Cp into temperature difference is the work done, and since we are talking of mass flow rates, the rate of work done is so much. Of course, your turbine has some efficiency, let us say efficiency of the turbine, and therefore this is the power of your particular turbine. Let us satisfy ourselves, let us make sure whatever we are writing, total mass flow mCp into delta T is the enthalpy which is dropped in your turbine, which is the work done by the turbine. And how did we say, but we are not talking of mass, we are talking of mass flow rate, therefore this is the power of the turbine, rate at which work is being done, or this is I can also write as W dot T, right. Can you tell me what is the work done by the two pumps? We have been doing it in the last class also. Rate at which work is done by the two pumps, which is equal to the power of your two pumps, is what? Let us say the unit is watts, joule per second. How do I write it? Let us take a look at this. It takes fuel, increases the pressure from this value to this value. Let us say that the increase in pressure is delta P, Newton per meter square, let us say Pascal. And what is the work done by these two pumps? The work done by a pump can be written as delta P into the volume flow rate, where delta P is the pressure rise across the pump and volume flow rate means the volume, the rate at which flow takes place through the pumps. The volume flow rate through the pump corresponds to the flow of the oxidizer and the flow of fuel, namely m dot oxidizer in terms of so much kilogram per second divided by the density of the oxidizer plus m dot of the fuel divided by density of the fuel. This is the volume flow rate of the fuel, this is the volume flow rate of the oxidizer, and this therefore multiplied by delta P across the pump is equal to the work required to run the pumps. If I look at the units, delta P has units of Newton per meter square, and these have units of kilogram per second, kilogram per meter cube, that means meter cube per second, which is equal to Newton meter per second or something like joules per second, or it is equal to something like watts. This is the rate of work required for the pumps. See, for the present, to have a simple analysis, I have assumed that the pressure increase in the two pumps is the same. Otherwise, I have to have a separate expression for this, a separate expression for this. I am just trying to illustrate the method. Yes, I have assumed that the pressure increase across the two pumps are the same, which need not be the case, right? It's whatever you are saying is true. Okay. Now, if this is so, I now say that my efficiency of the pumps is eta P, and therefore the total work done is so much, work required is so much, because my efficiency of my pump is small, therefore I have to divide it, and therefore now I equate the rate of power required for the pump with what is the work which is available, and therefore now I write delta P into, I write this as equal to m dot O by rho naught plus m dot fuel divided by rho F into 1 over eta P is equal to whatever I got over here, let us simplify it and write it, is equal to m dot O into your Gg plus m dot F into your Gg into Cp eta T into whatever we have, let us take Tgg outside, 1 minus T outlet divided by Tgg, and this becomes my expression. How do I get the fuel fraction from here? Fuel fraction we said was equal to the fraction which is going into your gas generator divided by the total. Therefore, maybe let's simplify this a little bit more. Let's rewrite it in the following way: m dot O into 1 over rho naught plus m dot O, no, let us take m dot F outside, in which case it becomes a little simpler, m dot F into 1 over rho F plus m dot O by m dot F is your overall mixture ratio into the value of rho naught, is it all right, into 1 over eta P is equal to, same thing I use again, I take m dot F going through your Gg over here, and now I write 1 plus Rgg into, I get the value of Cp eta T Tgg, and now I say temperature. If I assume isentropic expansion in your turbine, T outlet by Tgg or T1 by T2 is equal to P1 by P2 pressure ratio to the power gamma minus 1 by gamma, or rather this becomes 1 minus 1 over the pressure ratio to the power gamma minus 1 by gamma. How do we do this? We know that the value of therefore this becomes, I can write this as P gamma V gamma by T gamma, and therefore now if I have to substitute, if I divide one by the other and I want to eliminate, I get P to the power gamma minus 1 divided by T to the power gamma is a constant, or rather P1 to the power gamma minus 1 by T1 to the power gamma minus 1 is equal to P2 and all that. Therefore, I get T1 by T2 is equal to, I get and this is what I set as a pressure ratio. Okay? No, let's go slowly, but let's do things completely. Therefore, if now I have to simplify this expression, what I have here, what is it I get? I get the value of m dot of the fuel through your gas generator divided by m dot of the total fuel which is going is equal to, now I take eta p on this particular side, say the product of the turbine efficiency and your pump efficiency is total eta. That means I take this by this, therefore this comes here, or rather let me invert it, m dot f by m dot gg is equal to, so that it becomes eta over here, which is equal to, eta is equal to pump efficiency into your turbine efficiency, m dot f, m dot g comes over here, and on the right hand side I therefore have eta into 1 plus mixture ratio in your gas generator into, I have whatever I have written here, Cp into Tgg into 1 plus the pressure ratio in your particular pump divided by gamma minus 1 by gamma, and I have to divide it by, let me divide it over here, which means I put this equal to over here, 1 over rho f plus the overall mixture ratio divided by rho 0. Is this okay? Please check whether we have left out any terms. Yes, where does delta p come? M dot f into this into delta p. That means here also we should have had delta p, here we swallowed the value of delta p over here, that means delta p over here. Okay. Where 1 minus? 1 minus r gamma minus 1 by gamma. Good. Anything else? Therefore, we are able to find out the value of m dot f by m dot o, but still what is it I want? I want to find out the fraction of the fuel which is going through your particular gas generator. What is it I am after? F is equal to m dot o or m dot oxidizer which is going through your gas generator plus m dot fuel which is going through your gas generator divided by m dot o plus m dot fuel, that means the net value of these two is the fraction. That means the fraction of propellants going through your gas generator divided by the total over here. Now this I again simplify as m dot o gg into 1 plus r gg divided by m dot o m dot f into gg into 1 plus m dot o gg by m dot f gg is the mixture ratio over here, m dot o gg, or let us again take m dot of f into 1 plus r. Please let's be very clear about it, and this is equal to your f. But what is it we have got here? We got m dot f by m dot o over here. Maybe I have to now convert it into some form wherein, yes, m dot f divided by m dot f gg, correct. Therefore, we have this, we have m dot f divided by m dot f gg divided by m dot f over here. Let us substitute the value, and what is it I get? I get the value as 1 over rho f plus the value of r divided by rho naught into delta p the value of eta into 1 plus RGG into Cp TGG into 1 plus Rp into gamma minus 1 by gamma 1 minus the value here, and this is equal to, I have to now get the value of m dot f multiplied by 1 plus RGG divided by, I now find into 1 plus R is equal to the value of f. I find that 1 plus RGG and 1 plus RGG gets cancelled, and therefore f is equal to 1 plus rho 1 over the density of the fuel, mixture ratio divided by density of oxidizer into the pressure drop divided by the net efficiency of your pump and turbine Cp TGG minus 1 by R into 1 over R is the net fuel value. 1 plus R. Cp into 1 minus 1 by R, okay, you are correct. Now I want to discuss these results. How do I do it? Maybe we will do it in the next class before I proceed further. Therefore, what is it we have done in this class? We wanted to calculate what is the fraction of the propellant which flows through your gas generator, and we have got an expression for this. We will quickly go through this expression and then we will see in what way to interpret the results. Thank you then, I think that is about it.